In A2, Unit 7, Lesson 1, we're going to analyze exponential functions. We're going to look at what they are, we're going to look at their general form, and we're going to look at what their graphs do. We're just going to be researching their form and their behavior. But before we get started with an exponential function, let's review real quick some rules about exponents that you may have forgotten. What is an exponent? Well, if I have x to the third, the 3 is your exponent, the x is your base. Now an exponent tells you how many times to multiply a base times itself. Versus if I have 3x, where 3 is a coefficient, this means x plus x plus x. So exponents mean multiplication and base and coefficients mean addition. Alright, let's look at some exponent rules. If I have x to the second times x to the third, I get x to the fifth. If I have x to the second to the third, I get x to the sixth. You multiply. Now if I'm multiplying numbers together, like 3 to the second times 3 to the third, this is just going to be 3 to the fifth. Multiplying matching bases never changes the base, because what you actually said here is, well, I've got 3 times 3 and 3 times 3 times 3. You've got 3 to the fifth. You don't have any 9s. So multiplying the bases, that extra base is absorbed in your exponent, but you don't ever change your base. You just match them. Alright, now, few more rules you may have forgotten. If you have a negative exponent, what that tells you is that your base is unhappy. It wants to go to the other side of the fraction bar. So if we have 2 to the negative 2 power, this is actually 2 over 1. So when I change it to make it happy, the exponent becomes positive, but it moves to the other side of the fraction bar. And we still have the 1 up here. So 2 to the negative 2 power would be 1/4. What if I had 1 over 3 to the negative 2? It still means it's unhappy where it is. So I need to move it to the other side of the fraction bar. That would be a 1 there. And 3 squared would be 9. So 1 over 3 to the negative 2 would convert to 9. And then last but not least, if you have any number raised to a 0 power, that is equal to 1. If you have a variable raised to the 0 power, that is equal to 1. And the reason is because of where that 0 comes from. How do you get a new exponent? Well, we got it from adding the exponents of two bases. Remember? X to the second times x to the third is equal to x to the fifth. Well, if you subtract, if I have x to the second over x to the third, division, you subtract exponents. So I would say 3 minus 2 is just 1 over x. One last rule. If you have any number raised to the 0 power, that is 1. If you have a variable raised to the 0 power, that is 1. Anything to the 0 power is equal to 1. And that's because where it comes from is, what happens if I have, say, x to the third over x to the third? When you're dividing, you subtract the exponents. 3 minus 3 is what causes you to have a 0 exponent. Now, what is any number over itself? Well, it's equal to 1. But you really just need to remember that anything raised to the 0 power is equal to 1. Now let's look at the definition of an exponential function. An exponential function is a function. First of all, what does that mean? Well, it means you have a relationship. So with the function, you're either going to have f of x equals something or y equals something. So with the function, you've got this. Now, it has a constant base. Well, we know what the base is. We know what a base looks like. What does constant mean? A constant is a number. It doesn't change. It constantly stays the same. So if I've got a constant base, let's just say 2, and a variable exponent. So this would be an exponential function. Now, versus if I have x to the second power, this is not an exponential function because my base is not a constant and my exponent is not a variable. So all you have to do to determine that it is an exponential function is make sure that your base is a number and your exponent is a variable. So being able to identify an exponential function is going to let you use all these rules and general forms and graphs that we're fixing to look at. An exponential function has what we call a parent function, and that's like a base form that we can manipulate, we can add to, subtract from, we can adjust it, but we have to have a parent form. And that parent form is f of x is equal to b to the x power, where b is your base and x is your variable exponent. Now, this could look like f of x is equal to 7 to the x power, or f of x is equal to 3 to the x power. We can even do some other things to it, like 3 to the x minus 1 plus 7. This has adjustments to it, which we'll look at the transformations later. But for now, the parent function of all these is just the base and its exponent. So like this one, your parent function is just f of x is equal to 3 to the x. Now let's just look at some of the characteristics of the graphs of a couple of different exponential functions. Now, along with the definition of the parent function, which is a constant term to a variable exponent, there are two other restrictions. B, your constant, has to be either greater than 1 or in between 0 and 1. And these are two different categories of exponential functions. If b is greater than 1, we have what we call a growth function. If b is in between 0 and 1, now what does that mean? Well, if it's a fraction, if it's 1/2 or 1/5 or 0.25, if it's less than 1 but greater than 0, then we have what we call a decay. Now, there's only two kinds of graphs. A growth function is going to look like this. Your decay function is going to graph like this. This is it, okay? It's one or the other. So all you have to do is look at your exponential function, find your b, and say, well, is it greater than 1? Because if so, you're going to have a graph that goes like this. If it's a fraction or a decimal, anything between 0 and 1, you're going to have a decay function like this. Let's look at these four examples. F of x equals 2 to the x power. Is this an exponential function? It has a constant base and it has a variable exponent, so yes it is. Is it growth or is it decay? Well, here's your base and this is greater than 1, so this one is growth. Alright, let's look at this one, negative 3x. You don't look at the negative part, you just look at this. So is this number 3 greater than 1 or is it between 0 and 1? Well, it's greater than 1. So this also is a growth function. Alright, here's 1/3 to the x power. 1/3 is not greater than 1. It falls in between 0 and 1. So this function is going to be decay. Now let's look at this one. 0.97. That's still less than 1. So it is also decay. So all you have to do to figure out whether something is growth or decay is find that base. Well, the easiest way to find the base is look for that variable exponent. So once you see the x, look down at its base. If it's greater than 1, you have growth. If it's in between 0 and 1, you have decay. Let's just look at one growth function and one decay function. We're just going to make a rough graph of it so you can kind of see the general characteristics of an exponential function. So remember, this is the only two possibilities that we have. Either b is greater than 1 or b is in between 0 and 1. So how do you graph a function? Well, you make your XY chart and pick some random numbers for X. I am going to pick -2, -1, 0, 1, and 2. Alright, now I'm going to fill these in one at a time for X, and I'm going to solve it and see what kind of numbers I get. Now remember, if I put -2 in, 2 to the -2 means I need to flip it, so I have 1 over 2 squared, which is 1/4. Alright, if I put -1 in, 2 to the -1 is just 1/2. If I put 0 in, 2 to the 0 power is 1. If I put 2 in, 2 to the first power is just 2. And if I put 2 in here, 2 squared is 4. Now let's graph that real quick. We're not going to be real specific about it. We just want to see the general trend. -2 and up 1/4, be about right there. -1 and up 1/2. Alright, 0 and up 1 is here. Over 1 and up 2. Over 2 and up 4. It's going to increase exponentially. So here is what happens. Okay, this shows growth. This is the typical exponential function graph. Now I want you to notice what happens to this graph as it goes along the x-axis. It's going to get closer and closer and closer, but it's never going to touch it. Okay, never going to touch it. No matter what number you put in here, you're not going to get y is equal to 0. So you're not going to touch that. We have a name for that, and that is called an asymptote. Asymptote. An asymptote is a line that is approached but never crossed. Okay? It's a line that is approached but never crossed. Now let's look at what happens when we graph f of x is equal to 1/2 to the x. Once again, I'm going to use the same x numbers, and we'll see what this does. If I put -2 for my exponent, I have 1/2 to the -2. Well, how do you make that exponent positive? You flip this. So now I've got 2 over 1 to the +2. When you flip it, the exponent is happy and it becomes positive. Now 2 to the first squared is 4. Alright, when I take 1/2 to the -1, I still flip it. And then it's going to have a +1 exponent. So that's 2. 1/2 to the 0 power is 1. 1/2 to the first power is 1/2. And 1/2 squared is 1/4. Now let's graph it right here and see what it does. I've got -2 and up 4. And then I've got -1 up 2. Then I've got 0 up 1. Over 1 up 1/2. And once again, you can see this line also is going to get closer and closer to the x-axis, but it's never going to touch it. So once again, my x-axis is my asymptote. So far, we have defined what an exponential function is. We've looked at the parent form, which is b to the x power, where b is a constant and x is an exponent. We talked about the fact that by definition, the b has to be greater than 1 and it'll show growth, or it can be between 0 and 1 and show decay. So let's just take a function. F of x is equal to 3 to the x power. Let's identify it. It does have a constant base with a variable exponent. And we're going to look just in general at how these exponential functions act, how they behave. We're going to find out what the domain is, the range, the end behavior, the y-intercept, and the asymptote. Because a lot of these things are going to happen to every single exponential function. So if I take f of x to the 3 to the x power, and I can rewrite this as y equals 3 to the x, and I want to graph it. and I'm going to do that. I'm just going to make an XY chart, and I'm going to pick those same five numbers. -2, -1, 0, 1, and 2. Now when I put -2 here, 3 to the -2 power is 1 over 3 squared, so that's 1/9. When I put -1 in, I get 1/3. When I put 0 in for this, I get 1. When I put 1 in here, I get 3. When I put 2 in here, I get 9. Just plug and play. All right, let's graph this. -2 and then up 1/9. That's just going to be a little, and we're not going to get real specific. We're just trying to look at its general behavior. So -1 over 1 and up to 1/3, be about right there, over 0 and up 1, over 1 and up 3, over 2 and up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So this is what our graph is going to look like. Now that we have it graphed, let's look at these characteristics, and we're going to see that these are very common to all exponential functions. First, I want to know the domain of my graph. Now the domain is the set of x values that you could find a point of intersection for. So if I look up and down my x-axis, everywhere I go up on the x-axis, I could find a point of intersection, because this graph just keeps on going this way and it keeps on going this way. Every single point on x would have a point of intersection at some point on the graph. And this is true whether you have a growth or if I had decay. It still goes all the way up and down the x-axis. So my domain is the set of real numbers. And this is true for every exponential function. All exponential functions have a domain of all real numbers. Now let's look at the range. The range is a little bit different because this graph only goes so far down. We're going to look up and down the y-axis this time. If I'm here and I look over, can I find a point of intersection? Yeah. What about down here? What about down here? Yeah. I have a point of intersection. Even right here, I could go to the left and find a point of intersection. Now when I get to the origin, to the 0, I'm not going to find a point of intersection because this graph never touches the axis. It gets closer, it approaches it, but it never gets closer. So my range is what? Y greater than 0. Because at y equals 0, I do not have a point of intersection. Alright, now your end behavior talks about what does this graph do at each end. You got two ends. You got the positive infinity end and you've got the negative infinity end. So as x goes towards positive infinity, f of x is talking about your graph. What is your graph doing? It's getting bigger and bigger too. Those values are getting larger. So as x goes this way, your graph or your y also goes towards infinity. Now let's look at what happens going this way. As x goes towards negative infinity, and this means as the numbers on x, all of these x's along your, all these numbers on your x-axis, what happens when you go to negative infinity? Well, your function approaches 0, but it never gets there. So what we're going to do here, f of x, this arrow means approaches 0. Now we need to find a y-intercept. You've been finding y-intercepts for a long time. You do it the same way. We're going to take y equals 3x, and I'm going to fill 0 in for x, because where does a y-intercept happen? Well, it happens at x equals 0. So if I let x be 0, I've got y to the 0 power, therefore y is equal to 1. So my y-intercept is at the point 0 and 1, and you can see that from our graph. Okay, your asymptote. This is the point where it doesn't cross. Well, here's our asymptote. So our asymptote is at y equals 0. okay? And that's all there is to finding the characteristics. And like I said, this is always going to be real. So your range will change some. Your end behaviors will be very similar, but sometimes they'll flip-flop. If I had decay, this would be the opposite. If I had a graph of something that was decaying, then as x went towards infinity, my line would get closer to 0. And here on the negative end, it would be reaching positive infinity. So that would flip, okay? All right, in the next lesson, we'll look at some more exponential functions, and I'm going to show you how to move these around.